Good afternoon, everybody. Welcome to lecture number 13. Again, I'm Professor Anant Agarwal at OSU, and I would like to acknowledge the support of my associate, Dr. Arash Salami, and of course, the funding from Office of Naval Research. Today, we introduce a new topic, and the new topic is Schottky diodes. This is a different diode than the PN junction diode we have been studying. So, Schottky diode was invented by Walter Schottky. In this case, we have a N-type semiconductor and we form a metal contact to the N-type silicon. So, if you remember the PN junction, we had a P plus semiconductor here and then the N-type semiconductor, and we formed a P plus N junction. In this case, we just form a metal semiconductor junction, and that's called the Schottky Barrier Diode. There are two types of diode characteristics. On the left, we show a diode characteristics where the current is high in one direction when the voltage across the diode is positive as applied to the metal, and in the reverse direction when the voltage is negative, the current is very small. So, it basically allows the current to flow in one direction. Then the second type of contact can be an ohmic contact between metal and semiconductor, which allows the current to flow in both directions. And in semiconductors and especially in power devices, we make use of both of these types of contacts. So, we will today describe what is the physics behind these diodes and the ohmic contacts. As I said, Walter Schottky his theories are behind the Schottky Barrier Diode. So, the Schottky Barrier Diodes have been named after him. He was born in 1986 in Zurich in Switzerland and passed away in 1976 in West Germany. He had studied under Max Planck, and then after that he had teaching and research assignments, and then finally worked at Siemens. So, he's known for many good research outcomes. He's credited with discovering the Schottky effect, which controls the emission of electrons from a heated electrode. So, that's the basis for vacuum tubes. He went on and invented the screen grid tube in 1915, and 1919 he invented the tetrode, the vacuum tube version of it. And then he was first to point out the existence of electrons and holes in semiconductors. And in 1935, he noticed a vacancy defect in semiconductor, which is named after him and is called Schottky defect. But in 1938, he developed the theory of Schottky diodes, that is the rectifying behavior of metal semiconductor contact. And when these Schottky barrier diodes were developed, they were named after him. So, a very brief history. I think you should look into it a little more. Walter Schottky was a very, very inventive person. So, here is schematically the diode construction. We are showing a metal contacting, in this case, an N-type semiconductor. It could also be a p-type semiconductor. We just happen to consider n-type semiconductors here because these are very common in power devices. And in this bottom we have plotted an energy band diagram of the Schottky diode in equilibrium. So, this energy band diagram will exist when we short the metal junction to the semiconductor junction with a wire. So, what happens when we short it? It turns out that the n-type semiconductor has a work function which is phi s. So, we measured the work function in semiconductors as the difference between the Fermi level to the vacuum level. And then there is an electron affinity chi, which is measured from conduction band to valence band. And then there is a metal work function phi m, which is measured from the metal Fermi level to the vacuum level. Now, if phi m is greater than phi s in the semiconductor, as we have assumed here, it turns out that the energy of electrons in the semiconductor is higher than the energy of electrons in the metal. So, remember, in the energy band diagram, as we move vertically in the y direction, the energy of the electron increases in the y direction. So, the electrons that are here in the conduction band have higher energy than the electrons in the metal, just because the work function phi m of metal is greater than the work function of the semiconductor phi s. So, in equilibrium, what will happen that some electrons will go to the metal because they have higher energy, and in doing so we will have a depletion layer built in such that there is a positive charge in the semiconductor in equilibrium because of this depletion. So, then there is an electric field set up and there is a negative charge in the metal. So, there is electric field set up from right to left, which counteracts the electron flow from semiconductor to metal, and it sets up a built-in potential which is called phi B for barrier, N for n-type semiconductor, phis of Bn. And this quantity is very important for the Schottky barrier diode. So, you can see that this barrier phi Bn is determined by the metal work function phi m and the electron affinity in the semiconductor chi. But in equilibrium, it is good to understand that electrons move from semiconductor into the metal side, leaving positive charge behind, which sets up an electric field which counteracts the flow of electron from semiconductor to metal. And in equilibrium, no net electron flow is happening, meaning no net current in this diode, and an equilibrium is set up with a barrier phi Bn inside the system, which is very similar to the built-in voltage we had studied in the case of p-n junctions. Okay. So, saying the same thing again, at zero bias, on an average, electrons going from right to left are equal to the electrons leaving from left to right, which means the net current is 0 and no current is flowing across this diode unless we apply an external forward voltage or reverse voltage. All right. So, now we have energy band diagram set up so that we have positive charge in the depletion region in this Schottky diode, a barrier height between the metal and the semiconductor, which is set up by the choice of the metal and the choice of the doping in the semiconductor or the type of the semiconductor, silicon or silicon carbide and what have you. There is another barrier shown here, it is phi bi, and that is the barrier on the semiconductor side. So, the electron here at the bottom of the conduction band will have to overcome this barrier to go from right to left as shown by the red arrow. So, this barrier simply depends on the metal work function minus the doping minus the position of the Fermi level EC minus EF, which depends on the doping of the semiconductor. Anyway, this barrier is not very important. This barrier is the most important barrier. So, as I said, the barrier from metal to semiconductor phi Bn depends on the type of metal we choose, because different metals will have different metal work functions phi m as shown here. Then we can choose different metal or we can choose different compounds of metal and silicon such as silicides, and each have a different work function, therefore, the different barrier height which controls the IV characteristics of these diodes. So, now supposing we apply a forward voltage across the diode, that means we bias the metal with positive voltage with respect to the semiconductor. So, if you can see this, what is happening in this energy band diagram, that barrier phi bi is reduced by the applied forward voltage V, and therefore, once this barrier is reduced, it is easier for the electrons to go from right to left. This is called thermionic emission over the barrier, and current starts flowing in the external circuit. That thermionic emission over the barrier theory has been developed, and the current depends on, so if we derive the current equation, it is given by I equals to I0 times e to the power q v over kt minus 1. So, this current equation is very similar to the equation we developed for the diodes, and whereas V is the applied voltage. So, remember, this is a very similar equation we developed for the PN junction diodes, where V was the applied forward voltage, I0 was the reverse saturation current. In the case of Schottky diodes, that reverse saturation I0 depends on the area of the diode. K is called the Richardson constant, and the units are given on the left hand side, centimeter square per Kelvin square, times the temperature in Kelvin times this exponent, where in the exponent we have the barrier height divided by Kt over Q. So, as I said, the characteristics of the diode depend on this barrier height, which is controlled by the metal work function difference, which can be tailored by choosing a metal. So, if we use a very high barrier height metal, high work function metal, then it will set up a higher barrier height, which means my I0 will reduce. But you can see if I0 reduces, then the forward current flowing in the diode in the case of forward voltage will also reduce. If we apply the reverse voltage, the opposite happens. But before we go to the reverse voltage case, let us reiterate that as we increase the barrier height by choosing a higher work function metal, the current in the Schottky diode reduces at a given forward voltage, and generally the forward current is defined by a knee voltage, which is very similar to the PN junction diode. Once the forward voltage exceeds the knee voltage, the current starts to rapidly increase in this diode. So, everything is controlled by this fundamental equation, which we have not derived for you, but I would encourage you to read some textbooks to see how this equation is derived. You can also see that the knee voltage is smaller than a knee voltage of a PN diode for a given semiconductor. So, in silicon, this knee voltage for PN diode is of the order of 0.7 volts. In silicon carbide, this knee voltage for Schottky diode would be of the order of 0.4 to 0.5 volts. So, you can see that Schottky diodes have a lower loss in the conduction process under forward bias, because the forward voltage drop for a given current is lower than what it would be for the PN junction diode. In silicon carbide, this knee voltage for PN junction is of the order of 2.7 volts. For Schottky's, that knee voltage is typically about 1 volt. Again, that knee voltage depends on the choice of metal, which determines this intrinsic barrier height inside the Schottky diode. Now, as you see in the reverse direction, this is I0, and you can see for PN junction, in the reverse direction, I0 is very small. As we reduce the barrier height, we get more and more reverse current flowing, because the I0 increases as we reduce the barrier height. So, for Schottky diodes, the fundamental trade-off is that by increasing the barrier height, we can reduce the reverse leakage current I0, but the forward losses increase because the knee voltage increases. And that trade-off is shown here. This figure has been taken from this textbook. You can see we have studied, they have shown the results from different metal silicides, platinum silicide, palladium silicide, nickel silicide, and chromium silicide, which have different barrier heights. and you can see platinum silicide has the highest barrier height and therefore has the highest knee voltage here, whereas chromium silicide has the lowest knee voltage on silicon, which is about 0.2 volts. PN junction for silicon would be at 0.7 volts, so the knee would be here. Then there are some examples of silicon carbide Schottky diode. These results were published in a paper, and they have been reproduced in Professor J. Baliga's book. You can see that here we have studied 3 different metals, ti, nickel, and gold for silicon carbide N-type material, and you can see that as we move from ti towards gold, the barrier height increases and therefore the knee voltage increases. So in this case, this IV plot has been plotted not on a linear scale but a logarithmic scale on the vertical axis. Therefore, we can then see more structure in the voltages versus current curve below the knee voltage. So in these cases, the knee voltage would be somewhere here for ti, so around 1 volt, nickel would be like 1.2 volt, and gold would be like 1.3 volts. That is the knee voltage. So we are looking at details of the current flow below the knee voltage, where the current is essentially controlled by thermionic emission of the barrier. And here we show that the barrier height as measured electrically tracks with the metal work function. The higher the metal work function, higher is the barrier height, and that happens to be true for silicon and silicon carbide. But it's not always true. If the contact region between the metal and semiconductor has a lot of defects and traps, then this is not true. But we are fortunate that it is true for silicon carbide. We can choose higher barrier height, higher work function metal, and we can get higher barrier height. So generally, most of the commercial silicon carbide Schottky diodes are formed with ti silicide or titanium, and then higher voltage diodes are formed of nickel. If you remember from what I said earlier, if you choose a higher barrier height metal, your barrier goes up, your forward conduction losses go up, but your reverse leakage current reduces. Then here we show 2 Schottky barrier diodes. This is again out of this paper. I encourage you to read this paper. You can see the current on the vertical axis, on the logarithmic axis versus the forward voltage for 2 metal systems, nickel and ti in silicon carbide. And you can see as we increase the temperature, I0 increases, and that's very understandable if we go back and look at the equation for I0. It's as we increase this temperature, this term reduces and this term increases, the prefactor increases, so the I0 increases rapidly with temperature, which then shows you how the forward current will increase because I0 is increasing. And also that means as we increase the temperature, the reverse leakage current, which is I0, will also increase. So you can see nickel has a higher barrier height, so the knee voltage is higher than ti, and just as we expected, and also the temperature dependence is as we expected. So, here what we have shown, and again these charts have been taken from Professor Baliga's book. We have plotted I0 versus the barrier height for different temperatures, and you can see as the barrier height increases, which is phi Bn in this equation, I0 reduces, and as we increase the temperature, the I0 increases. Same thing for silicon carbide for different barrier heights. As we increase the barrier height, I0 reduces, and as we increase the temperature, I0 increases. Then we come to the ohmic contacts. Ohmic contacts are the ones, if you remember from first slide, are the ones that follow the current, allow the current flow in both directions for positive voltage and for negative voltage. So, in that sense they are different from Schottky diodes. Schottky diodes are called also rectifying contacts because they conduct current in one direction and do not conduct in the reverse direction. So, the ohmic contacts in semiconductor are basically formed the same way, except we dope the semiconductor side very, very heavily. In this case, we have shown N++, that means very high doping. So, when that happens, you can see that the depletion width in equilibrium due to the barrier height phi Bn, which is set up, is very small, because a small amount of depletion will give you large amount of positive charge, which is needed to counterbalance this barrier height. Now, that means the electrons do not have to go over the barrier when we apply voltage. They can tunnel through this narrow barrier, and that means the current can flow both in the forward direction like it flows in the Schottky diode, also in the reverse direction by means of this tunneling. And also this tunneling can take place in either direction when we apply positive voltage or negative voltage. So, the current can easily flow in both directions by combination of tunneling and emission over the barrier, which is a fundamental Schottky current transport mechanism. And forming this diode is a little bit of art. Here we show in red line a good ideal ohmic contact between two. This shows you the current flowing between two contacts on an N-type semiconductor, and you can see as we increase the doping, we have an ohmic contact. As we reduce the doping, you can see you can form a rectifying contact. Now, it also depends on what temperature we have deposited the metal. So, this is the case of nickel on top of silicon carbide N+, and you can see if we do not anneal the nickel in high temperature, then we will not form the nickel silicide, and we will have rectifying characteristics between these two contacts. Now, if we anneal the contact at very high temperature, something like 900 degrees C, we will form what is called as the ohmic contact, because nickel would make a certain phase of silicide and we will have a good contact flowing. So, that case has been shown here in a very nice paper on the contact technology between nickel and silicon carbide on 4H silicon carbide, and my associate Dr. Arash Salmi is one of the co-authors in this paper. I would highly encourage you to read this paper if you're interested. Here we have deposited nickel on top of N plus silicon carbide, and we have annealed it at different temperatures from 500 to 950, and you can see as we anneal it at higher and higher temperature, the contacts become ohmic in nature, in the sense they allow free flow of electrons in both directions. So, at this point I will stop here. Thank you very much. Next time we will apply these Schottky diode theories to a practical high voltage Schottky diode. So, thank you very much.